In this video here, we're going to take a look at elastic energy. Now, another important skill for this chapter is that we know how to find the energy stored in an elastic string or spring. And if we draw a force distance diagram, such as this one here to show the extension x in an elastic string as a gradually increasing force is applied, then the area under the force distance graph, as we can see here then, is the work done in stretching the elastic string. Now just note here then that the applied force is always equal and opposite to the tension in the elastic string T, and this value increases as the string stretches. And for the area under the graph, we can easily derive this then by either considering the area of the triangle or by using integration. So to find the area here by using the triangle, right? So we need to find the area of the triangle, then the area here, A, is equal to the base divided by 2, so my base here is x, so I get x over 2, and let me times this by the height here. So the height then is lambda x over L. So if we put it all together then, what we simply get here is lambda times x squared all over 2L. Nice and easy, right? And then if we want to find the area by integration here, again, pretty straightforward stuff, right? So the area A here is equal to the integral then of T here, so T being the applied force with respect to S here, the extension, and we're integrating then over this interval here from 0 to x, so from 0 here to x. Now T then is simply lambda s over L. Again, we're integrating with respect to S here, and obviously my interval doesn't change. So if we evaluate this here then with respect to S, what we simply get here is lambda times s squared over 2L. Now, what we now need to consider here basically is what this would be once we substitute in our limits, right? So basically just replace s with x here. Obviously the 0 has no effect, right? It just gives you 0. And in that case then, this just evaluates to give us lambda times x squared over 2L. And again, you should get the exact same here. If you don't, then clearly something's gone wrong, because no matter what, you should get the same result here. So to finish with here then, let's just summarize everything that we need for elastic energy. So to summarize here then, the work done in stretching an elastic string or spring of modulus of elasticity lambda from its natural length L to a new length here, let's just say L plus x, is given as lambda times x squared all over 2L. And don't forget then, this result here we just derived on the previous page. Now this rule applies if the extension is within the elastic limit of the string or spring. And when lambda is measured in newtons and x and L are measured in meters, the work done then is given in joules. So this here is just an important point to be aware of. Now when a stretched string is released, it will essentially just ping back to its natural length. And in its stretched position, it has the potential to do work, or essentially this is what we just call elastic potential energy, which again, we can also just call here elastic energy, right? Which is the whole point of this video. As we can see here, elastic energy. Now, the elastic potential energy, which we often just abbreviate to EPE here, stored in a stretched string or spring, is exactly equal to the amount of work done to stretch the string or spring. And the EPE stored in an elastic string or spring of modulus of elasticity lambda, which has been stretched from its natural length L to again a new length here, let's just say L plus x. Again, it's just given as lambda times x squared all over 2L. Again, this here is just the exact same result as this one here, and the result that we derived on the previous page. And we can also apply the same formulae for work done and elastic potential energy when an elastic string or spring is compressed, right? And you'll see exam questions and just general practice questions here where you have an elastic string or spring that is compressed. So just so you're aware here as well that it also works for, an elastic string or spring being compressed. So to finish with here, let's just work through two examples together. So let's just get started then with question 1 here on elastic energy. So for this question here, all things considered, it's a pretty straightforward question. What we've got then is an elastic string which has a natural length of 1.6 meters, and we're also given the modulus of elasticity, which is 8 newtons. So for this question then, all we want to do here is just find the energy stored in the string when its length is 2 meters. So like I said, pretty straightforward, right? What you need to be aware of here is the formula then for energy being stored here in the string. So energy stored here. So energy stored is equal to, so it's equal to lambda times x squared all over 2L. So I've got lambda times x squared all over 2 times L. So lambda here, that's the modulus of elasticity. So x here, that is the difference then in the natural length and the length that we're given here, so what it's stretched to, which in this case here is 2 meters. And then L here just represents what we call the natural length, right? So putting that all together then here, what do we get? So lambda is 8. I've got 8 here times by x squared. So what is x here? So when the string is stretched then, it goes to 2 meters. The natural length is 1.6 meters. So the difference here is 0.4 meters, right? So I do 8 times 0.4 squared. So 8 times 0.4 squared. And that's all over then 2 times L, where L here, again, just represents the natural length, right? So 2 times 1.6. And at this point here, like we said, right, nice and straightforward. Just put this into your calculator. And if you do this correctly then, what you should find here for the energy stored in the string then, when its length is 2 meters, is we get 0.4 joules here. So don't forget then, this is energy. So the correct units here are joules. So 0.4 J there. Okay. So to finish with then, the energy stored. So the energy stored in the string when its length is 2 meters is, as we got here, right, 0.4 joules. Okay. 0.4 joules there. And there we have it then. So, like I said, quite a nice, easy question just to get us started. But there we have it then. So that gives us the solution here to question 1. And then to finish with here, we have the very last question, question 2. Now for question 2, then what we're told here, what we're told then is a light elastic spring has a length of 1.5 meters and a modulus of elasticity of 8 newtons. So one end of the spring is attached to a fixed point and a particle of mass 2 kilograms is attached to the other end and hangs in equilibrium. So for this question then, all we want to do here is just find the energy stored in the spring. A very typical exam style question here. So you don't have to, but what I would do here to begin with is just draw a quick diagram, right? It doesn't need to be a masterpiece. If you've ever watched any of our previous videos here, you will know then that my art skills are pretty shocking for the most part, but we'll give it a go here. Let's see what we end up with. So I've got something here, which will give us our fixed point, right, for the spring then. I've got my fixed point here, like so. So the spring is attached to this fixed point, right? Let's just say here, okay? So the spring will go down like so. Clearly that should just be a straight line. I'm doing it freehand. It's never the easiest, but just go with it. We've then got the particle here that's attached to the other end. So I'll just kind of draw that on like so, and we'll shade that in. Bosh, good stuff. Let's just keep going here. So underneath then, what I've got here is the mass of the particle, right, which is 2 kg. So acting downwards then, our force here is 2g newtons. So I'll just denote that as 2g here. What we've also got then in the spring here, opposing the mass then, is the tension in the spring, right? And that will act vertically upwards, okay? We've got the tension here, T newtons. So that's all we need for the diagram here. Again, you don't have to draw a diagram, but I do think it's always, you know, a good habit to get into here for mechanics questions. So what do we know then for this question here? Well, we've got the natural length, we've got the modulus of elasticity, and we also have the mass then of the particle. So to begin with here, what I'm going to do then is just resolve here vertically. So resolving vertically here, taking upwards as positive. Well, what I've got here is an equilibrium problem, right? So forces acting upwards will be equal to forces acting downwards, right? Just basic A-level maths and A-level mechanics here, or mechanics from A-level maths, I should say. So in that case, then T here, so T is equal to 2G, right? Very basic stuff. But what we can now do here, again, because it's an equilibrium problem, is use the fact that T, the tension here, is equal to lambda times X divided by L. So just recall then when we first introduced Hooke's law here for equilibrium problems, T then, so let me just make a note here. So we're now going to use then that T here, the tension, is equal to lambda times X all over L, okay? So what do we know here? So lambda, don't forget lambda, is just the modulus of elasticity, so that's just 8 here. L is the natural length, which is 1.5. What we want to do here then is just solve for X, right? We know what T is 2G. So putting that all together then, what I get here is, I get 8x, so 8x over L, which is 1.5. So we've got 8x over 1.5 is equal to T, where T is equal to 2G. Perfect. Okay. Again, all we want to do here is just solve for X, right? So basic stuff then, just times both sides by 1.5. So 8x equal to 3G. And in that case, then X here, so X is equal to 3/8 of G. Okay, like so. If you evaluate this here, what we get then is 3.675. But as we work through the question, it'll just be easier to keep this in exact form anyway. But if you want the decimal equivalent, there you go. So what we're looking for here is the energy stored in the spring. So don't forget then, we did cover this in the previous question then, question 1. If you're looking for the energy stored here, so therefore energy stored here, so energy stored, we need to use the following formula. So energy stored then is equal to lambda times x squared all over 2L. Okay, so what we're going to do here is just put all of this together now, right? So lambda is still 8, right? That doesn't change here. That's just the modulus of elasticity. So I get 8 times by x squared. So x here is 3 over 8g, or 3.675. Again, just keep life easier here, or make life easier. Just keep this in exact form. So what I've got here is 8 times by 3 over 8g, like so. And don't forget, we square this here, like that. And then this here is all over 2L. So L here is just the natural length of the spring. So 2 times 1.5. Good stuff. At this point here, just use a calculator, right? You don't get bonus points for doing this by hand, so just use a calculator here. If you do this correctly, then what you should get here is 36.015, so on and so on. And in that case, then, what we get here for the energy stored in the spring is simply 36 joules. Okay, so I'll just do this underneath here. So therefore, then, the energy stored in the spring is simply 36 joules there. Okay, again, this is energy. We use joules here as our units. Okay, and there we have it then. So hopefully, this question here, this explanation, this demonstration here has helped. As I said, a very typical exam style question here on elastic energy. But I do think here, all things considered then, this is, a pretty nice question, right? I don't think there's anything particularly too challenging about this. It's just using the basic concepts here then of Hooke's law for equilibrium problems and elastic energy. Okay, but there we have it then. So that gives us the solution here to the very last question, question 2. And that brings us to the end then of this video here on elastic energy.